Greetings, Doctor. This is Stephen Magezi, and I am presenting a high-level paper summary for a paper that was assigned to me called Hybrid Quantum Enhanced Federated Learning for Cyber Attack Detection. The paper implementation, the paper entirely looked at how to classify cyber attacks that are happening on a daily due to technological advancements. The paper proposed a hybrid federated learning-based cyber attack detection model that was categorized into 4 integrated sections. And the sections are hierarchical model aggregation procedure, spatio-temporal attention network, quantum-inspired federated averaging model, and privacy preserving techniques. In the next slides, I am going to expound on each of these modules. And then one is the hierarchical model aggregation. The HMA is a procedure presented to enhance the stability, accuracy, and the efficiency in the model, whereby it operates in a decentralized learning environment, whereby nodes run independently, and these nodes are grouped into regions based on their network condition and data similarity. And from the visualization here is there are different nodes that run the data independently, but they are clustered into regions based on network and data similarity. Now here in the visualization, the edge servers aggregate local model updates before sending them to the global server. In a different environment, they can be multiple models whereby they are trained independently, and after they are aggregated hierarchically to form a stronger predictor. And now the stronger predictor is the global model, because the regional servers feed into the local nodes that run. They send their updates to the regional server, and then regional servers, they send their updates to the global model. Second feature is the spatio-temporal attention network STAN. The spatio-temporal attention network STAN allow for the precise extraction of complex temporal and spatial patterns from the data, a feature that is adaptable to various databases and applications beyond network security. From the visualization here, network traffic data that comes into the model is divided into 2 types, the temporal vector and the spatial vector, and this data goes through a series of interventions, whereby this data is critically analyzed to extract all complex patterns from it, and after it is concatenated and further sent out as an output for other deeper layers in the model. Now, from the visualization here is it captures both spatial and temporal dependencies in the data, making it particularly useful for sequential and structured information processes. And from the visualization here, it leverages attention mechanisms, and attention mechanisms selectively focus on the most relevant spatial and temporal features, which improves the various tasks. Third feature is quantum-inspired federated averaging, QIFA. The learning process here is this feature enhances the learning process by adapting a quantum-inspired federated averaging procedure, which is based on principles of quantum computing, and these principles are superposition, entanglement, and decoherence. The major aim of incorporating the quantum principle is to enhance aggregation and convergence of the federated learning model. Now, quantum-inspired federated averaging is after data has gone through the STAN network. At the end of this process, this data has to be aggregated and converged to get an output, whereby this output is used as input in the next layer of the model. Now, quantum-inspired federated averaging is it can be represented mathematically in a formula that you can see, whereby from this formula we can calculate the inspired federated averaging to have a more accurate output. Just a breakdown of the formula is that this is the formula where K is the total number of nodes that are running independently, and the formula is a product of the quantum-inspired coefficients and the local model parameters after training with the data at node K. The quantum-inspired federated averaging algorithm works in a way that each client or each node trains its private data set, and then model weights are then transferred into the quantum-inspired federated averaging using the formula represented. And the fourth feature is privacy preserving techniques. In order to ensure privacy in the federated learning module, differential privacy and secure multi-party computation techniques were incorporated into the module. Now, to implement the differential privacy, the local node model updates are added with a Gaussian noise factor before sharing these updates with regional nodes. And the Gaussian noise factor can be represented mathematically in the formula below, whereby the Gaussian noise factor is the last formula that is added to the formula. Maybe to expound more on the privacy preserving techniques, is these techniques add a noise factor which prevents attackers from identifying the individual data that is being sent, and this can be done locally or globally. Now, at local level, noise is added before data is sent to the central server. Now, at local node, our central server can be the regional servers. Globally, noise can be added to aggregated results or model updates. Now, after our local nodes have executed the different patterns from the data, and they've sent updates to the regional servers. Now, at aggregation of the output before it is sent to the global model, noise can be added at that point before sending. That is the global noise addition. And here is the key idea is instead of sending raw data to a central server, users train models locally and share only updates. Effectiveness and innovation in the solution that was proposed is that the solution has high accuracy and recall in cyber attack detection, whereby it had very high values of accuracy and recall precision, because from the graphical representation of the recall and precision values, we realized that our hybrid module was ranging the highest from all other traditional models, because it includes the STAN, which improves pattern recognition of convolutional neural networks, It also incorporates the QIFA, which enhances model convergence and optimization. It also has the HMA, which reduces communication overhead, especially whereby this data is the models operate independently. Another effectiveness and innovation in the paper is the novel combination of federated learning and quantum optimization. From the results, it has superior performance compared to other traditional models. It also offers enhanced privacy and efficiency and adaptability to the data that is being transferred from the local models to regional servers and then to the global model. Limitations and future work from the paper is a limitation. Limitation number one is increased computational cost due to quantum principles. We all know that quantum computing requires high hardware resources, which require specialized hardware and specialized technology and specialized people to handle. So it is a good innovation, but it comes with a cost. Another limitation from the paper was scalability challenges with large networks, because we all know as is a component of sharing updates from the local node to the regional servers, from the regional servers to the global server that updates the global model. Now, in there, as the network grows bigger and wider, there will always be scalability challenges, especially from the interconnectivity. Another challenge is quantum-inspired modules may require specialized hardware, as I had explained earlier, and also is quantum models require computational complexity, which increases due to multiple techniques. You realize that our proposed model is a hybrid model that incorporates the STAN feature, the QIFA feature, and the HMA feature. Now, as complexity increases, it also calls for multiple techniques. Feature work from the paper proposed adaptive learning to improve real-world deployment of this model. I think from the paper there was no real-world application of this model, and there were no future plans. The paper didn't highlight future plans where this model can be applied. That can be a talking point for researchers. Another feature work proposed in the paper was future improvements can focus on scalability and real-world implementations. Thank you so much.